I'll say term. So for example, here's some single term things. Let's talk about their degree. X. What's the degree on X? What's the power? 1. Okay, so degree is equal to 1. So it's a monomial. It's a monomial because it's one single chunk, one piece, one term, but the degree on there, the power is a 1. 3x squared, what's the degree on this? You got it. Still a monomial, right? Still a single piece. We don't have like different pieces with pluses or minuses in between, just one piece. And the degree is 2. What about this one? Notice you don't add powers on the number, just the variable powers, right? Like the x and y and stuff like that. This is a combination one, right? To get the total degree on this, you add the 2 and what's on the y? Okay, so degree is what? You got it. Now, why would we ever care about something like degree? Let me tell you. The idea is that degree controls the shape of what you're looking at. Remember how in the previous chapter you saw stuff like y equals 2x, right? You've seen this before in the past. If I look at this piece right here, what's the power on x? What's the degree of that term? 1. How many curves are in a line? There's no curve. A line's straight, right? Degree equals 1. And you have no curves. Okay. Has anybody ever seen a parabola before, like x squared? Here's a single term for you, x squared. This is what it looks like. Let me remind you, you've seen it before, but we haven't really officially learned it. I just drew it for you one day in notes. Something like that, right? What's the degree on x squared? Okay, degree is equal to 2. How many curves do I have? Just 1, right? Huh. But there's a relationship. I bet the degree can help me predict how many curves if I can see the pattern. Let's see, with a degree of 1, there's none, because 1 minus 1 is 0. With a degree of 2, how many curves? Because 2 minus 1 is 1. If I had a degree of 3, what would I expect? How many curves? 3, right? The reason that we would even point out the degree, this idea, before we even start playing with exponents and stuff in this chapter, is because that right there is what's going to fuel the shape of your picture. It's going to be what tells you what to look for. Now, when you start mixing x and y, it gets a little bit more complicated because you're making curves on the x way and making curves in the y way. You're getting three-dimensional stuff here. But the main basic idea that I just want to point out to you for fun is, hey, guys, the reason they're torturing you and saying learn how to tell me the degree is because as a modeling person in mathematics, you know what your model is going to look like before you even draw it. You might not know how high it is. You might not know if it's upside down or moved left or right. But you can at least know how many curves to look for when you're looking at significant stuff on the picture. This will be important in 080 when you start trying to solve models if you're using your calculator. Because sometimes when you draw a picture, you might miss part of it. For example, if I had graphed this one over here on the right and I only got the right-hand side of that line, I'd say, oh, I should probably zoom out my calculator picture. I'm not seeing the whole thing. You see what I'm saying? It makes you more powerful because you know what you're supposed to see. You can make sure you're getting the right picture when you're using technology and things like that. That's the idea of degree. This is a type of polynomial where you just have one piece. We'll talk more about polynomials next class, though. For tonight, we're really just going to focus on dealing with powers, not so much on this part. This is just kind of a fun introduction. You'll have to find degrees, but that's not your main thing. This is just like an introduction to what a monomial is. Let's see. So the first thing we need to talk about is how to deal with exponents multiplying and dividing. So let's talk about multiplying exponents. And I'm going to warn you guys that these steps are so easy, but at the same time, it's one of those that can kind of trip you up if you don't practice them a lot. So we're talking about how to handle powers, how to reduce things, specifically multiplication. And then we'll do division in a second. Multiplying is the easiest one. You'll like it. I'll teach you through an example. Let's say you had two monomials being multiplied. Keep using this word because it really doesn't matter. I want you to be comfortable with it, that I'm not giving you a vocab test. If you had x squared times x to the fourth. What? Now remember something, guys. If I had this exact same problem with a plus sign in the middle, could I do anything? Could I? Are they like terms or not? Something to a squared and something to a fourth. Are these like terms or not like terms? Not like terms, are they? So I could not have added or subtracted x squared plus x to the fourth or x squared minus x to the fourth. You can't do that. Let me write that. Recall, if you've had a similar situation, you can't do anything. Because they're not like terms. But in this case, we're doing something very different. We're multiplying them. So we can do this. In multiplying and dividing, guys, you don't really care that much about like terms. Actually, what you care about is your base number. You care about that right there. So for multiplying and dividing, actually, I'll put and dividing, we do need or want same bases. You know, remember when we were talking about similar stuff with that power on there that we would have been picky about with adding? We're not picky anymore. In fact, let's look at it and see what it is. Let's break it down into its parts and see if we can deal with it. What does x squared mean, guys? X times what? Oh, x times, okay. What does x to the fourth mean? And what are we doing in the middle again? Multiplying. Oh, hello. Maybe that's why we care about those similar bases. I'll show you more examples in a second to help prove it to you. Since they're all x's, since they're all the same thing, how many of them do I have? 6? Okay. So I could rewrite this as x to the 6, right? So we just said that x squared times x to the fourth is the same thing as x to the 6? Huh. Very cool. Again, noting that they both had x's as those bases. Let's look at a mixed up example where the bases don't match, so I can kind of prove to you guys why we would even care about that. Remember in your evaluations, this was the best class ever, except the technology didn't work? She wasn't the best. Remember. I'm just kidding. Okay. So, here's another example for you. We have, let's use a different letter just for kicks. A squared times B cubed times B, I don't know, to the fourth. So we'll count those up, even though it makes no difference. So I've changed the letters on you, but the same idea, right? You guys know exponents. That just means, how many A's do I have being multiplied? 2. A times A. Okay. So we know that even if it's a number or a letter, that the exponent just means that you have that many of it, right? So here we have A times A. Sounds good. Times what? 3 B's. Okay. B times B times B times what? 4 b's, more b's. Okay, b times b times b times b. What in the world? Now, of course, you're not usually going to write something out that long, but you know, we could condense it now and write it, if we just for fun, because remember, it's like a puzzle. I'm teaching you how to pull it apart and put it back together. In a second, I'll show you the shortcut so you don't have to do this every time. But for right now, while we're playing, how can I rewrite this as an exponent? A to the what? Okay. Good. And b to the what? So it doesn't matter what the base is. It doesn't matter what that big number on the ground is, whether it's an X, a B, or whatever. If it matches, what do I do to those exponents when I want to combine them? Just add the powers. Yeah, 2 plus 4, X to the 6th. B to the 3rd, B to the 4th, B to the 7th. But what happens if the base doesn't match? Like here, the A, it didn't match the B's. Did anything happen to it? No, you just attach it on there. You keep it together. That's fine. We're not that picky. You can keep it just, you know, it's like a snowball. You stuck it on the side. But you don't put it together because they're still different. Different pieces. But for the B's, you can lump them together a little bit better. You can add those exponents. So when you're multiplying, for same bases, I'm writing the bases again because that's really significant, guys. When you have the same bases, add your exponents. And that's when multiplying. Let's look at some more complex stuff then. It's more complicated multiplying. It's still fun, totally fun. Just keep that in mind while you're doing this. Okay. Let's say I had negative 2 x to the 3rd times, as you know, 4 x to the 5th. So really, all we have is multiply, right? Negative 2 times x cubed times 4 times x to the 5th. I mean, even though we're not showing the symbol between that negative 2 and the x cubed, there's an invisible multiply there, isn't there? You don't have to show me this, but I'm showing you why. Multiplication order doesn't matter, does it? So I can say negative 2 times 4. What is that? Negative 8. Oh, yeah, and then I can actually simplify this. What is an x cubed times an x to the 5th? X to the what? 8th, is that what you said, Alex? Good. Negative 8, x to the 8th. That was another example. So if you have numbers in there, just multiply your numbers together and then do the same stuff for the variables, for the letters. The same pattern you just saw. 2 times 4 is 8. They had opposite signs, so we kept the negative. And then when you add the powers, the 3 plus a 5 gives you an 8 on that x. Be okay?